Let's go over some review questions for Chapter 2, dealing with light. And try yourself out on this. Which of these is not a form of electromagnetic radiation? We have gamma rays, infrared, sound, visible light, radio. Well, all these are electromagnetic radiation except for sound. Sound is a pressure wave within air or a gas, and so you can't hear sound unless you have that pressure wave, and it's much slower, much less energetic in general than electromagnetic radiation. Try this. The distance between successive wave crests defines the blank of a wave. Well, if you're looking at successive wave crests from peak to peak, you're looking at the definite spatial distance between the repetition of a wave. We define that as the wavelength of the light from crest to crest, or actually any point to any equivalent point. The next successive equivalent point is a wavelength for a wave. Question 3. The frequency at which a star's intensity is greatest depends on its... The frequency at which a star's intensity is greatest depends on its... Well, this is mentioning the frequency of the greatest intensity, but if you were to map the intensity as a function of frequency, you would have a skewed black-body curve, and so the maximum of that curve would correspond through Vienne's law to the temperature of the object. Here we can see a black-body curve for the sun, and we can see that the peak occurs in the visible spectrum, which tells us something about the light from the sun, and also tells us the temperature of the surface of the sun from Vienne's law. Hotter stars produce much more high-frequency light. Question 4. Rigel appears as a bright bluish star in the constellation Orion, whereas Betelgeuse appears as a bright reddish star in the constellation Orion. You can see the constellation down here. Rigel and Betelgeuse are exactly opposite. You can see definitely the red star Betelgeuse, the blue star Rigel. Question is, Rigel is blank Betelgeuse. Well, what you're looking at is the limits within the visible spectrum, and there may be higher or lower energies associated with that star that you can't see, but within your frame, what you're seeing is that the best indication you get from Betelgeuse is that's on the red side of the spectrum. Rigel's on the blue side. Blue is higher energy, hotter than red. So Rigel is hotter than Betelgeuse. Its maximum may not be in the blue, but it may even be in the ultraviolet. Here's question number 5. If a light source is approaching you, you will observe, well, if something's approaching you, the source is approaching you, you should expect that if it has a spectrum, that spectrum will be shifted, and it should be shifted to a higher frequency. It should be blue shifted. Let's see how we got it here. Question A, spectral lines are red shifted. No, that would be if it were moving away from you. B, the light is much brighter. Not necessarily. If it's far away, brightness is not going to change. C, the spectral lines are shorter in wavelength. That's another way of saying it's blue shifted. If you say you have a higher frequency, you're going to have a shorter wavelength. That's the answer, a shorter wavelength. Question 6. The wavelengths of emission lines produced by an element. Well, we talked about the wavelengths of emission lines produced by an element is kind of like a fingerprint of that element. And let's see what we got here. A depends on its temperature. are identical to absorption lines. Yes. And you can see that fingerprint if it emits as an excited gas or if it absorbed just those frequencies from a continuous spectrum. So the lines involved for these transitions of energy are the same lines in either case. Same transitions, same energies, same frequencies. So the wavelengths of emission lines are the same as the wavelengths of absorption lines. Question 7. Analyzing a star's spectral lines can tell us about all of these except, well, we can get a lot of information from light. And from the spectral lines we can get its composition. We can get its surface temperature from Wien's law. We can get its rotation from the Doppler shift and its density from the spread of the spectral lines. We can't get its transverse side-to-side motion. That's transverse to the motion. That's not either forward or away, or towards us or away. So we have to use a different technique to figure out its transverse side-to-side motion. So we can't get that. Question 8. What types of electromagnetic radiation from space reach the surface of the Earth? Well, we're being bombarded through the whole spectrum of electromagnetic radiation, at least the Earth itself. But fortunately for us, our atmosphere protects us from most of that radiation. So we actually have a shield in different layers of our atmosphere. Very important shield, the ozone layer, the magnetosphere, the clouds, everything protects us from different frequencies of light that reach the Earth. But there are two windows, and if you're trying to do astronomy from the surface of the Earth, you could look through those relative frequency windows, and what you would be able to do is look through the visible light by using visible astronomy. There's a window for that. And radio astronomy. If you're doing radio astronomy, you'll be able to see radio waves. So our two windows through our atmosphere is visible light and radio waves. You can see those windows down here in the electromagnetic spectrum on this diagram down here. Question number 9. Which of the following has a fundamentally different nature than the other four? We got A, proton, B, electron, C, neutron, D, atomic nucleus, E, photon. Well, the proton is matter, electrons matter, neutrons matter, atomic nucleus is matter. The photon is a bundle of light. It is a particle, but it has no mass. So it is the particle associated with light. It is fundamentally different from matter itself. So the photons are packages of light bundles, and fundamentally different from matter. That concludes this quick quiz on Chapter 2.